In this video, we will learn all about the cross product, which is the second of our vector products. Now the cross product is a bit more tedious than the dot product, since our output is going to be a vector instead of a scalar. So to start, how do we define the cross product? Given two vectors u being u1, u2, u3, and v being v1, v2, v3, then the cross product is u cross with v vector bracket. Since we're going to get out a vector, it's going to have three components. The first component is going to be u2 v3 minus u3 v2. And if your u's and v's are really hard to separate, maybe you just replace a's and b's in your notes, right? You can make those adjustments because they're your notes. The second component is going to be u3 v1 minus u1 v3. And the third component of the cross product is going to be u1 v2 minus u2 v1. Now, this is going to be a bit challenging to try to memorize, but don't worry, we're going to have a better way to organize the cross product and actually do out the computation. But by definition, this is the cross product. U cross v is the vector u2 v3 minus u3 v2, u3 v1 minus u1 v3, and u1 v2 minus u2 v1. Okay, so we start with three-dimensional vectors. Our output is also a three-dimensional vector. And more importantly, the cross product is only defined for three-dimensional vectors. And the product is a vector, unlike the dot product, where the product was a scalar. Okay, so this is the second vector product. We can see the formula up above. Now, to understand the cross product spatially, we use something called the right-hand rule. Right-hand rule. And the rule says we point our fingers in the direction of the first vector so that we can curl towards the second vector. The direction your thumb points will be the direction of the cross product vector. Okay, so taking my right hand here, I would rotate it so that the palm of my hand would be facing the second vector. So I point in the direction of the first vector, I curl towards the second vector, and my thumb would be pointing in the direction of the cross product vector. Now, just holding my hand in front of the camera, while you might understand the words and the actions, it's a little bit hard to understand what we're actually defining. So let's look at an example. So compute k cross I. So if we take our axes, right, so we have x, y, and z. So we have unit vectors I, j, and k. Okay, so let's see how good of an artist I can be. So we're going to point our fingers on our right hand in the direction of k. Okay, so 1, 2, 3, 4. And our palm is going to face I, since that's the second vector. So that means our thumb is going to point that way. So again, fingers go in the direction of k. Our palm is facing I so that we can curl, right? Curl our fingers down, and our thumb would go in the direction of j. So that means k cross I is j. So if we look at my very artistic diagram, if we were going to do k cross negative I, right, k cross negative I, well then we would have to flip our right hand. So instead of the palm facing towards us, towards the positive I axis, we would need to flip our hand so that the palm faces away, which means that our thumb would be over here now, pointing in the direction of negative j. And this is going to take a bit of practice. One thing that is important, make sure you're using your right hand. I know it sounds silly, but there are times that I see students using their left hand because their pen is in their right hand and getting all crossed up and confused. Okay, so right hand rule, fingers go in the direction of the first vector, curl towards the direction of the second, thumb goes in the direction of the third. Okay, and that thumb represents our cross product vector. okay, which also emphasizes the fact that we're taking two vectors defined by a cross product, and the output is a third vector. Now, we're going to take a little detour through linear algebra to create a better way to compute the cross product instead of that formula that we wrote on the first slide. In order to do that, we have to talk about the determinants of matrices. So some of you might be familiar with finding determinants, others might need a refresher, and some might remember it perfectly. So the determinant of a 2 by 2 matrix is, so remember, a matrix is just organized numbers. So then we have a 2 by 2, 2 rows, 2 columns. The lines mean determinant, so our determinant is going to be AD minus BC. Right? And the reason we need to define a 2 by 2 determinant is we're going to use that in finding a 3 by 3 determinant. So the determinant of a 3 by 3 matrix can be done in two ways. I'll show you both, and then it's down to a matter of preference. So cofactor expansion. So the idea here is we go along a row or a column, and we create smaller 2 by 2 matrices that we can find the determinant of. So expanding across the first row, since that's typically what we'll do for the cross product, it's going to look like this. A, and if we cover the first row and the first column, what's left right in here is a 2 by 2 matrix, E, F, H, I. And then minus B, so then we cover this first row, second column now, and what's left is a 2 by 2, D, F, G, I. And then plus C, cover the first row, third column, D, E, G, H. And then we would compute the three smaller 2 by 2 determinants, so A times EI minus FH minus B DI minus FG plus C times DH minus EG. And we could distribute out the A, the B, and the C. Now, in terms of why the B is negative, when we're talking about cofactor expansion, every entry in the 3 by 3 matrix has an associated sign. So in a 3 by 3 matrix, I'll come over here to the right, it would be plus, minus, plus across the first row, and then minus, plus, minus, and then plus, minus, plus. We don't need to go this far. Really, I'm just doing this for some completeness. Since using this technique for the cross product, we are only going to be expanding across the first row. And you'll see why when we get to that point. Now the diagonal method, we're going to take the first two columns of the matrix and rewrite them next to our determinant. So A, D, G, B, E, H. So what we've created is a much larger matrix now. And I'll grab a highlighter. So we're going to go down the forward diagonals. So that's going to give us, don't want a crayon, right? AEI plus BFG plus CDH. So we find the product along the diagonal, and then we add it to the product of the next diagonal plus the product of the third diagonal. And then minus, take a different color. Now we go down the backwards diagonals, the three complete backwards diagonals. So that's going to be minus, and then we're adding the blue diagonals together, the products along each. So CEG plus AFH plus BDI. And we can compare the two. So this first term here, AEI minus AFH, if we were to distribute. AEI minus AFH. And we can go term by term and see that we would get the same value. Okay. Determinants don't give us vectors, right? This is a scalar value. So how are we going to expand upon this idea to incorporate the cross product and get a vector out of the determinant. So let's look at that. The cross product of vectors u and v can be expressed as, so u cross v is equal to, so it's going to be the determinant of a 3 by 3 matrix. Along the first row, we're going to put the components, the 3 unit vectors, I, j, k. Then along the second row, we'll put the components of u, so u1, u2, u3, and then along the third row, v1, v2, v3. Since I, j, and k are unit vectors, and we'll wind up just getting scalars of I, j, and k that are combined with addition or subtraction, that will give us a vector out. Okay, so this will be the setup that we use in order to use the method of finding a determinant to find the cross product of two vectors. We could expand this out with u's and v's, but let's put numbers in. It's going to make our life a lot easier. So find u cross v if u equals 2, negative 3, 5, and v equals negative 1, 2, 4. So u cross with v, so we're going to set up our matrix. So I, j, k across the first row. So then 2, negative 3, 5, negative 1, 2, 4. Now the order does matter. We'll define that in a few slides, but we have to put u as the second row and we have to put v as the third row because it's u cross v. If it were v cross u, we would have to put v as the second row and u as the third row. And now I'm going to use cofactor expansion. So I times, so we cover the first column and the first row, so the matrix is negative 3, 5, 2, 4, and then minus j, and the matrix is going to be 2, 5, negative 1, 4 when we cover first row and the second column, and then plus k, which will be 2, negative 3, negative 1, 2. So we find the determinant, so we get negative 12, so I, negative 12 minus 10, minus j, 8 minus negative 5, so plus, and then plus k, 4 minus 3. So we get negative 22i minus 13j plus k as our cross product vector u crossed with v. So now, follow up to the cross product question is they want us to find a dot product. So they're asking us to find u cross v dotted with u and u cross v dotted with v. So u cross v dotted with u cross v dotted with u. So it's going to be negative 22 times 2, so negative 44. And then negative 3 or negative 13 times negative 3, which will be plus 39. And then 1 times 5, which will be plus 5. Negative 44 plus 44, that's going to be equal to 0. Now let's look at the other dot product they ask us to find, u cross v dotted with v. So negative 22 times negative 1, so positive 22. Negative 13 times 2, so minus 26. 1 times 4 is plus 4, which will be equal to 0. So we took the cross product vector, we dotted it with vector u and vector v, and we got 0 each time. Now thinking back to our video on the dot product, that means that these vectors are orthogonal or perpendicular. So that means the cross product vector is a vector that is perpendicular to both u and v. And that trait of the cross product vector is one of the most important, and it will be something that we build off of as we continue through this course. So the cross product vector is orthogonal to both original vectors. Write perpendicular in your notes if that's helpful. So now find u cross v if u equals 4i plus 2j plus k and v equals I minus j plus 3k. So I'd like you to pause the video, try this cross product on your own, either the cofactor expansion or the diagonal method, and then check back in. Okay, so u crossed with v is equal to I, j, k, right? As I said before, order matters. So 4, 2, 1, 1, negative 1, 3. So for this example, I'll use the diagonal method, just so we have one of each in our notes. So I, 4, 1, j, 2, negative 1. I'll grab the highlighter. So forwards diagonals, there's 3. I'll just highlight everything first. So, and then green, the backwards diagonals. Okay, so forwards, the yellow, we get 6i plus j minus 4k, and then minus the green, so 2k minus I plus 12j. So we have 6i plus I, so 7i, j minus 12, so minus 11j, negative 4k minus 2k minus 6k. Right, so there is our cross product vector using the diagonal method. If you use the cofactor expansion method, you should still get the same. Personally, I use the cofactor expansion method. I just find once you practice it enough, it is a bit faster, but really whichever method you prefer works. Okay, properties of the cross product. So let u, v, and w be vectors, and c be a scalar. Okay, so the first thing we spoke about in the previous 2 slides is that the order of the cross product matters. So u cross v is not equal to v cross u. It is equal to the negation of v cross u. Right, so if we switch the order of our cross product, we wind up with a negation of our vector, our cross product vector. Okay, so for instance, if u cross v is 1, 1, 1, then v cross u would be negative 1, negative 1, negative 1. All right, if we're going to scale the cross product vector, we could choose to scale u first and then cross it with v, or we could choose to scale v first and then cross it with u. All 3 of those will give us the same answer. If we have the 0 vector cross with a vector v, we will get the 0 vector. Right? Imagine setting up your determinant with a row of zeros. Right? You'll get all zeros as your component. Remember, 0 vector, not 0 the number, 0 the vector. And then v cross v, if we cross a vector with itself, we will also get the 0 vector. Again, I would encourage you set up a matrix where the second and the third row are the same vectors and do the cross product out and see what you get. You should get a vector with all components being 0. Now u cross v plus w, so crossing over vector addition. Cross product is distributive, so u cross v plus u cross w, right? So this is the distributive property. So it's not commutative, but it is distributive. And if we change, so the sum, vector addition happens first before the cross product, still distributive, but make sure the order stays the same. So it's u cross w plus v cross w, right? We have to be concerned with the order that we expand in. And then u dot v cross w, so if we have a dot product of a cross product, that is equivalent to u cross v dotted with w, right? So just changing the order would get the same thing. This is called a scalar triple product. You have to be careful about the order. Sometimes we might get the negation, okay, but this is something that when there's numbers involved, we can play around with a little bit more. And then u cross v cross w. So this property is a little less used, but I like to include it because we get to see the connection between the cross product and the dot product. So u cross v cross w is equivalent to u dot w times v, right? Remember that's a scalar, minus u dot v times w. So essentially, cross product of a cross product turns into an expression with a dot product, right? So just tying together the 2 vector products in a nice way. like I said, a little bit less used, but nice to see. So now talking about the magnitude of the cross product vector. If theta is the angle between vectors u and v, then the magnitude of u cross v is equivalent to the magnitude of u, the magnitude of v, times sine theta. Now, why that's the case, we'll look at in the problem set. There's a problem that will address it, and will confirm this to be the case. But what I want you to notice is magnitude turns this into a scalar, and if we relate it, u dot v, right, the dot product, just for comparison, the dot product, u dotted with v was equal to magnitude of u, magnitude of v cos theta. The cross product's magnitude is magnitude of u, magnitude of v sine theta. So, find the magnitude of u cross v if the magnitude of u equals 3, the magnitude of v equals 7, and the angle between u and v is pi over 4. Okay, so they give us all of the necessary information. So magnitude of u cross v is 3 times 7 times the sine of pi over 4. So that's going to be 21 times the square root of 2 over 2, which if we want to write this as one term, 21 square root of 2 over 2. Okay. And if they give us vectors, right, we can find the angle. A little bit harder to find the angle using this definition. The dot product would probably be the easier way to go. Two vectors, u and v, are parallel if and only if u cross v is equal to the 0 vector. So this one's not too bad to show. I would encourage you to play around with this. Remember, if two vectors are parallel, that means they're scalar multiples. So that would mean that, let's say, v is equal to some scalar multiple of u, and put that into a cross product and evaluate and see what you get. You should get the 0 vector. And then you can try to work backwards as well and see if you can confirm it. Okay, but two vectors are parallel if they're scalar multiples, or another way to show that vectors are parallel is to show that their cross product is the 0 vector. Now, the magnitude of the cross product can be used in other types of problems. So we can use the cross product to compute areas of parallelograms and triangles. So the magnitude of the cross product of u cross v is equal to the area of the parallelogram determined by u and v. Okay, so what that's saying is the magnitude of u cross v is the area of this parallelogram. Now, the how behind it, area of a parallelogram, right? Area is base times height. So let's drop a perpendicular down. That's the height. Now, the base in this example, the length of the base, would be the magnitude of u, right? So the base is the magnitude of u. The height, if I come over here, height, well, let's start with just a right triangle relationship. So that means that, I'll erase actually h equals, give me some more space. So h is opposite of theta and v is the hypotenuse. So sine of theta equals h, which is a scalar, over the hypotenuse, which is the magnitude of v, right, the magnitude of that vector. So that means h is equal to magnitude of v sine theta. So magnitude of v sine theta, well, that's the definition of the magnitude of u crossed with v. So if we have a cross product vector and we want to know the area of the parallelogram formed by those two vectors, we just have to find the cross product vector's magnitude. And then if we expand upon that, if we want the area of a triangle that has sides of u and v, right, so I'll go into the diagram. Imagine I have a triangle, two of the three sides, one is vector u, one is vector v, then the area of that triangle is going to be half the area of the parallelogram. So 1/2 of the magnitude of u crossed with v. So given points, A being 1, 0, 1, B 2, 2, 2, C 4, 2, 2, and D 3, 0, 1, determine the area of the parallelogram ABCD. So just a reminder as far as labeling a parallelogram, if we start A here, right, A, B, C, D, we work either counterclockwise or clockwise around the parallelogram. Okay, so we need two vectors. So let's define vectors AB and AD. So vector AB, terminal minus initial, so 1, 2 minus 0 would be 2, 2 minus 1 would be 1. AD, so 3 minus 1 is 2, 0 minus 0 is 0, 1 minus 1 is 0. So that gives us a few nice numbers. So we're going to find the cross product. Now the order doesn't matter because ultimately we will be taking the magnitude. So we'll just go AB crossed AD, 1, 2, 1, 2, 0, 0. Now I'm going to run through this quickly, but feel free to pause the video and try this on your own and check your answer. So we're going to get 0i and then minus j, 0 minus 2. So 0 minus 2 is negative 2, but negative j, so plus 2j. And then k will be 0 minus 4, so minus 4k. So you can see I walked through the cofactor expansion without actually writing anything out. And again, that's just practice and doing this over and over again. Magnitude of AB crossed with AD is equal to the square root of 0 squared plus 2 squared plus negative 4 squared. So 4 plus 16 square root of 20 or 2 square root of 5. So if we want the area of triangle ABD, so if we drew that diagonal right across the parallelogram, so that's going to be 1/2 times the area of the parallelogram. So 1/2 times 2 square root of 5, so square root of 5. Right? So easy extension to find the area of the triangle. Now we can expand this into 3 dimensions. So the scalar triple product, one of the things that we looked at in the properties, can be written as a determinant. So instead of doing V cross U, V cross W, and then dotting it with U separately, we can do it in one step. So instead of that first row being IJK, the first row will be vector U, then the second row will be vector V, and the third row will be vector W. Right? So we replace first row with vector U. And then we go through either the diagonal method or the cofactor expansion, and we don't get a vector out this time since there's no I, J, or K across the first row. You'll get a scalar, right? And that makes sense because there is a dot product part of this expression. Now, the volume of a parallelepiped formed by the 3 vectors is defined as the magnitude of U dot V cross W. And really it's an absolute value since dot product is a scalar. So what that means is the scalar triple product can be used to find the volume of a parallelepiped. Now that word is new. All that means really is a prism that has faces that are parallelograms, like you see in the diagram here. If the scalar triple product is 0, then vectors are coplanar. Basically that means that the parallelepiped has no volume, and that's only going to happen if this vector that's coming off of the plane is actually on the same plane as the other 2. So if this was vector U, this was vector V, this was vector W, right? The volume of the parallelepiped would be the area of the base times the height. Area of the base is V cross W. And then the height, right? So that is V cross W, that vector there. And if we project U onto V cross W, so using a scalar projection, as we did in the last video, we're projecting U onto that green vector. So that's going to be U dotted with an area of the base. I put parentheses, but I did mean magnitude, so I do need to adjust that. So magnitude of V cross W, and then times U dotted with V cross W over the magnitude of the vector we're projecting onto, All right, so there's that projection there. That's the height. So magnitude of V cross W. Magnitudes cross out, and we are left with the fact that volume equals U dot V cross W. Okay, so easy enough to show, and it's nice because it does incorporate that scalar projection that we talked about earlier. So let's look at one last example to actually find the volume of a parallelepiped formed by the vectors. So we can cross two of them and then dot, or we can do it all in one piece. So we can use the scalar triple product, so A dot B cross C. So that's going to be 2, 0, 1, 1, 1, 1, 0, 2, 2. Again, pause the video to practice your cross product computation, but I'll walk through it with cofactor expansion again. So 2 times the determinant of this matrix, which is 2 minus 2, which is 0, and then minus 0, so the matrix is irrelevant, plus 1 times the matrix, or the determinant here, so 2 minus 0, which is 2. So that's going to be 2. And remember, we are looking for the absolute value of that. In this case, doesn't matter since we got a positive value anyway. But that means the volume formed by these three vectors is 2. If we got 0 out, what that tells us is these three vectors are in the same plane. So we covered a lot in this video, and I told you to start. The computation for the cross product is a bit more tedious, so the problems took a little bit longer. The application of the cross product is torque. We're not going to focus or look at it in too much depth, but I think it's important to mention that torque, if you're in a physics class, is a nice application of what we're doing in this video. So practice with either the diagonal or the cofactor expansion method, because finding cross products is going to be something that we do throughout this course. So we have to get pretty good at it.